Welcome! In this session, we'll explore an interesting coding problem titled Champagne Tower, which challenges us to simulate the flow of champagne in a pyramid of glasses. We'll break the problem down, analyze different approaches, and understand how to optimize our solution. Let's dive in. Imagine we have a champagne tower, where glasses are stacked in rows. The first row has one glass, the second row has two glasses, the third row has three glasses, and so on. Each glass can hold exactly 1 unit of champagne. When we pour champagne into the topmost glass, it starts filling up. Once the glass is full, any excess champagne spills evenly into the two glasses directly below it. This process continues down the tower row by row. Now, given the number of champagne units poured into the topmost glass, we need to calculate how much champagne ends up in a specific glass, identified by its row and position within the row. If the glass is completely empty, the result will be 0. If it's completely full, we return 1. To solve the problem, we are given 3 inputs. First, poured, which is the total number of champagne units poured into the topmost glass. Second, query_row, the row number of the glass we are interested in, where rows are numbered starting from 0. Finally, query_glass, which specifies the position of the glass within the specified row, also starting from 0. The output is a floating point number representing the amount of champagne in the target glass. If the glass is empty, we return 0, and if it's full, we return 1. Let's look at some examples to better understand how this works. In the first example, we pour 1 unit of champagne into the topmost glass. Since the topmost glass can hold exactly 1 unit and does not overflow, no champagne spills into the glasses below. As a result, all the glasses in the second row remain empty. Specifically, the glass at row 1, position 1, contains 0 units of champagne. Therefore, the output is 0.0. Now, consider the second example where we pour 2 units of champagne into the topmost glass. Here, the topmost glass becomes full with 1 unit, and the remaining 1 unit overflows evenly into the 2 glasses directly below it. This means each glass in the second row receives 0.5 units of champagne. For the glass at row 1, position 1, the amount of champagne is 0.5 units. Thus, the output is 0.5. In the final example, we pour a very large amount of champagne, specifically 100,009 units. With such a large volume, all glasses in the first 33 rows will be completely filled, each holding exactly 1 unit of champagne. This includes the glass at row 33, position 17, which will also be full. As a result, the output is 1.0. Looking at the constraints, we see that the number of champagne units poured can go up to 10 to the power of 9, and the query is limited to glasses within the first 100 rows. This ensures that the problem remains computationally feasible. Additionally, edge cases, such as no champagne poured or extremely large values for poured, are also accounted for in the problem constraints. To solve the champagne tower problem, one straightforward approach is to simulate the flow of champagne row by row, starting from the top. Imagine pouring the champagne into the topmost glass and letting it overflow down to the glasses below. To implement this, we use a 2D array, where each element represents the amount of champagne in a specific glass. At the beginning, we initialize the top glass with the total amount of champagne poured. Then, for each glass, if the amount of champagne exceeds its capacity of 1 unit, the excess, or overflow, is split equally between the 2 glasses in the row below. This process continues until the target row and glass are reached. Finally, we return the minimum of 1 unit or the champagne in the queried glass since no glass can hold more than 1 unit. While this approach is simple to understand and implement, it requires significant memory because we maintain the entire champagne tower in memory, even though only the current and next rows are actively being used during the simulation. To address the memory inefficiency of the brute force approach, we can optimize it by reducing the space required to simulate the champagne flow. Instead of storing the entire tower, we only keep track of the current row being processed and the next row that will receive the overflow. This is accomplished using 2 1D arrays, one for the previous row and another for the current row being calculated. Initially, the top glass in the previous row is set to the total champagne poured. Then, for each row, the current row is reset to 0, and the overflow from each glass in the previous row is calculated if it exceeds 1 unit. This overflow is then distributed equally to the corresponding glasses in the current row. Once the computations for the current row are complete, it becomes the new previous row for the next iteration. This way, we reuse memory efficiently and avoid storing unnecessary data. When we reach the target row, the champagne in the queried glass is returned, ensuring that we only use memory proportional to the number of glasses in a single row. Both the brute force and optimized approaches share the same time complexity of O(n squared, as we still need to process each glass in the tower up to the target row. However, the space complexity is significantly reduced in the optimized approach, dropping from O(n squared to O(n), because only 2 rows are stored at any given time. While this space-optimized method is slightly more complex to implement due to the need to manage row transitions carefully, it is far more memory efficient. This makes it the preferred strategy, especially for larger row numbers where memory constraints could become an issue. The optimization is based on the key observation that champagne flows strictly downward, so we never need to revisit previous rows. By reusing arrays for the current and next rows, we achieve the same result as the brute force method without the overhead of storing the entire tower. This balance of clarity, performance, and memory efficiency makes the space-optimized approach the ideal choice for solving this problem in a practical and scalable manner. The problem involves simulating how champagne flows in a triangular tower of glasses. At the top level, you start by pouring a specific amount of champagne into the single glass. Each glass in the tower can hold a maximum of 1 unit. Any overflow from a glass splits evenly between the 2 glasses directly below it in the next row. This process continues row by row, and your goal is to determine how much champagne ends up in a specific glass, identified by its row and column. To solve this, we simulate the flow using a step-by-step approach. First, we need to understand how champagne propagates, starting from the top and flowing downward. This behavior mirrors how overflow is distributed row by row. Next, we use a 2D array to represent the tower. Each cell in the array corresponds to a specific glass, and its value represents the champagne amount in that glass. The array's size is determined by the number of rows we need to compute, which is the query_row plus 1. Initially, all the glasses are empty, so the entire array is filled with zeros. To begin the simulation, we pour champagne into the topmost glass by setting the first cell of the array, tower, 0, 0, to the total amount poured. From there, we simulate the flow of champagne row by row. For each glass, if the amount exceeds 1 unit, the overflow is calculated as the excess divided by 2. This overflow is then distributed to the 2 glasses directly below, one to the left and the other to the right. Specifically, the overflow is added to the values at tower, I plus 1, j, for the left glass and tower, I plus 1, j plus 1, for the right glass. The current glass is then capped at 1 unit, as it cannot hold more than that. Once all rows up to the query_row are processed, the simulation is complete. The result for the target glass is simply the minimum of 1 in the value in tower, query_row, query_glass, ensuring that no glass exceeds its capacity even in the output. This approach relies on a few important insights. First, the champagne only flows downward when a glass overflows, so we save computations by focusing only on glasses with more than 1 unit. Second, the use of a 2D array simplifies the simulation since we can directly access and update values for each glass and its adjacent ones. Additionally, the simulation can terminate early if no glass in a row overflows, as this means subsequent rows will remain empty. For data structures, the 2D array is the core component, with its size proportional to query_row plus 1 x query_row plus 1. This ensures simple and efficient access to each glass. In terms of complexity, the time required is proportional to the number of glasses in the triangle, which is roughly query_row(2). Similarly, space usage is also O query_row(2) due to the size of the array. However, this can be optimized to O query_row by only storing the current and next rows at any point. This balance between simplicity and efficiency makes the approach both practical and scalable. For example, suppose we pour 4 units of champagne into the tower, and we want to find the amount in the glass at row 2, column 1. We first initialize the tower with all glasses set to 0. After pouring, the topmost glass holds all 4 units. Since its capacity is just 1 unit, it overflows by 3 units, which are split evenly between the two glasses below. This updates the second row to hold 1.5 units in each glass. Moving to the next row, the first glass in row 1 overflows by 0.5 units, splitting 0.25 units to each of the glasses directly below. Similarly, the second glass in row 1 overflows by 0.5 units, adding another 0.25 to each of its lower neighbors. At this point, the target glass at row 2, column 1 has accumulated a total of 0.5 units. To complete this example, we can visualize how the champagne levels stabilize after the simulation. The topmost glass is capped at 1 unit, and the overflow from it fills the glasses in row 1, each also capped at 1 unit after distributing their excess. Finally, the glasses in row 2 receive the distributed overflow. Specifically, the glass at row 2, column 1 ends up with 0.5 units of champagne. This is the final result that we return. By following this systematic approach of pouring, simulating overflow, and capping each glass, the problem is effectively solved with clarity and efficiency. This solution begins by creating a 2D array, tower, to represent the champagne tower. The size of this array is determined by query_row, with each row containing one more glass than the previous. For example, row 0 has 1 glass, row 1 has 2, and so on. The amount of champagne poured into the top glass is stored in tower 0, 0. The algorithm then iterates through each row up to query_row. For each glass in the current row, if the amount of champagne exceeds 1, indicating overflow, the surplus is evenly distributed to the two glasses directly below it. This ensures that each glass holds at most 1 unit of champagne, and any excess flows down the tower. Finally, the solution returns the amount of champagne in the specified glass, query_glass, of query_row. Since a glass can hold at most 1 unit, the value is capped at 1 using the min function. This ensures correctness when handling cases where the glass is fully filled but not overflowing. The algorithm efficiently handles the problem within the constraints, ensuring all edge cases, e.g., no overflow, partially filled glasses, are addressed. The use of a 2D array allows for straightforward tracking of champagne distribution across the tower. This is the Java implementation of the LeetCode problem number 799, Champagne Tower. The logic mirrors the Python implementation, where we simulate the pouring of champagne into a 2D array representing the tower. Key differences include type declarations for variables, the use of Java-specific syntax for arrays, and the math library for operations like math.min. The solution efficiently computes the champagne levels in each glass row by row, ensuring proper handling of overflow. To solve this problem, we start by initializing the champagne tower as a 2D array. Since the query is about row 1, we need 2 rows, row 0 and row 1. Initially, all glasses are empty, so the tower looks like this, 0, 0, 0. Next, we pour 2 units of champagne into the top glass at tower 0, 0. After pouring, the state of the tower updates to 2, 0, 0. Now, we process row 0. The top glass at tower 0, 0 contains 2 units of champagne, but since each glass can hold a maximum of 1 unit, the overflow is 2 to 1, which equals 1. We retain 1 unit in tower 0, 0 and distribute the overflow equally between the two glasses below it, tower 1, 0 and tower 1, 1. Each glass receives 0.5 units of champagne, and now the tower updates to 1, 0.5, 0.5. Finally, we query the champagne in tower 1, 1, which is 0.5. Since it's less than 1, the result is 0.5. In this example, we pour 4 units of champagne and query the amount in row 2, glass 1. First, we initialize the champagne tower. Since the query involves row 2, we create an array with 3 rows, 0, 0, 0, 0, 0, 0. Initially, all glasses are empty. We then pour 4 units of champagne into the top glass at tower 0, 0, which updates the tower to 4, 0, 0, 0, 0, 0. Now, we process row 0. The top glass at tower 0, 0 contains 4 units, so the overflow is 4 to 1, which equals 3. We retain 1 unit in tower 0, 0 and distribute the remaining 3 units equally between tower 1, 0 and tower 1, 1. Each glass receives 1.5 units, and the tower updates to 1, 1.5, 1.5, 0, 0, 0.
Next, we process row 1.
Starting with tower 1, 0, it contains 1.5 units, so the overflow is 1.5 to 1, which equals 0.5. We retain 1 unit in tower 1, 0, and distribute the 0.5 units equally between tower 2, 0, and tower 2, 1.
Each of these glasses receives 0.25 units.
Similarly, tower 1, 1 also contains 1.5 units, so the overflow is the same, 0.5. We retain 1 unit in tower 1, 1, and distribute another 0.5 units equally between tower 2, 1, and tower 2, 2. The updated tower is now 1, 1, 1, 0.5, 1, 0.5.
Finally, we query the amount of champagne in tower 2, 1.
This glass contains exactly 1 unit of champagne, which is the maximum it can hold.
Hence, the result for this query is 1.
In the next example, we consider a smaller input where only 1 unit of champagne is poured, and we query row 2, glass 1. First, we initialize the champagne tower with 3 rows, 0, 0, 0, 0, 0, 0. All glasses start empty. We then pour 1 unit of champagne into the top glass at tower 0, 0. Since this is exactly the capacity of one glass, there is no overflow. The tower updates to 1, 0, 0, 0, 0, 0.
Now, we process row 1.
Since there is no overflow from the top glass, no champagne flows into the glasses in row 1. Both tower 1, 0, and tower 1, 1 remain empty, so the state of the tower stays the same, 1, 0, 0, 0, 0, 0.
Finally, we query the amount of champagne in tower 2, 1.
Since no champagne reached this row, the glass remains empty with a value of 0. Therefore, the result for this query is 0. The time complexity of our solution is primarily determined by the nested loops that simulate the champagne flow through the tower up to the specified query underscore row. First, the outer loop iterates through each row of the tower. Since the tower only needs to be simulated up to the query underscore row, the outer loop will run query underscore row times. Inside this, the inner loop processes each glass in the current row. For row R, there are R plus 1 glasses. If we sum the total iterations of the inner loop across all rows, it forms a series, 1 glass for row 0, 2 glasses for row 1, 3 glasses for row 2, and so on, up to query underscore row plus 1 glasses for row query underscore row.
This is the sum of the first query underscore row plus 1 integers, which can be computed using the formula, query underscore row plus 1, asterisk, query underscore row plus 2, slash 2.
Since this sum grows quadratically with query underscore row, the overall time complexity is O, query underscore row caret 2. Now, each iteration of the inner loop involves only constant time operations, such as checking for overflow or updating the values in the champagne tower.
Because these operations do not add extra complexity, the time complexity remains O, query underscore row caret 2.
Moving on to space complexity, the memory usage is determined by how we store the champagne tower. Specifically, the tower is represented as a 2D list where each row contains R plus 1 glasses. Summing up the total number of glasses across all rows gives the same series as before, 1 glass for row 0, 2 for row 1, and so on, up to query underscore row plus 1 glasses for row query underscore row. Using the formula for the sum of the first query underscore row plus 1 integers, the space required for the tower is also O, query underscore row caret 2. Since we don't rely on any additional large data structures, the auxiliary space usage is minimal, or O1. Therefore, the overall space complexity is dominated by the 2D tower, resulting in O, query underscore row caret 2. In comparison to a brute force or naive approach, which might simulate the champagne pouring process for a much larger tower regardless of the query underscore row, our solution avoids wasted computation. By constructing only the rows up to query underscore row, we save both time and space. This optimization ensures that we focus only on the relevant portion of the tower. While this approach is efficient, there is room for further improvement in space complexity.
For example, instead of maintaining the entire 2D tower, we could use a single list to represent the current row and update it in place as we process each row.
This would reduce the space complexity to O, query underscore row. However, regardless of such optimizations, the time and space complexities remain O, query underscore row caret 2, in all cases. Since the algorithm always processes a fixed number of rows up to query_row, there's no variability in performance based on specific inputs. As a result, the best, average, and worst-case scenarios all have the same complexities. Finally, the mathematical justification for both time and space complexities is rooted in the triangular number formula. Each row of the tower contains R+1 glasses, and the total number of glasses up to row query_row is the sum of the first query_row plus 1 integers. This sum is calculated as query_row plus 1 asterisk query_row plus 2/2, which grows quadratically with query_row. Because this growth is proportional to the square of query_row, both the time and space complexities are O, query_row 2. This formula and its quadratic growth explain why the complexities scale as they do, providing a clear theoretical foundation for our analysis. In this section, we'll discuss some common mistakes to watch out for when solving the Champagne Tower problem.
First, a frequent issue is incorrectly propagating the excess champagne. Remember, when a glass overflows, the champagne splits evenly between the two glasses directly below it. Forgetting this rule can lead to an inaccurate distribution throughout the tower. Next, it's important to handle edge cases properly. For example, if the target glass is empty or the amount of champagne poured is too small to reach it, failing to account for these scenarios might result in incorrect answers or runtime errors. Another common error is accessing indices outside the bounds of the tower array. This can happen when simulating the flow for larger inputs and will lead to runtime crashes. Lastly, some people misinterpret the problem requirements by assuming champagne overflows only when the glass is completely full, ignoring fractional overflows. This misunderstanding can cause errors in the calculations for how champagne flows into the next row. Now let's focus on a few additional mistakes and some key insights for tackling this problem effectively. Inefficient implementations are another area to be cautious about. While a two-dimensional array is intuitive, it's not memory efficient. Instead, you can optimize by reusing a single row, significantly reducing memory usage. This is especially helpful for large towers. From an interview perspective, it's important to understand the concept of cumulative propagation, where each glass's overflow contributes to the next row. Breaking the problem into smaller, manageable steps can simplify your approach. To optimize further, consider using just 2 rows or even a single row with a temporary buffer to save memory. This is a simulation-based problem that requires you to model the process step by step, so recognizing patterns and understanding why the solution has a time complexity of O(n²) will be key. This complexity is manageable within the problem's constraints, so be prepared to explain it during an interview. Next, let's explore related problems that share similar concepts. LeetCode 935, the night dialer, involves dynamic propagation across a grid-like structure and is conceptually similar in how updates spread across the state space. LeetCode 64, minimum path sum, also requires cumulative calculations row by row, making it comparable to how champagne flows through the tower. LeetCode 119, Pascal's triangle 2, is another closely related problem, as both involve simulating row-based updates with opportunities for optimization. Finally, LeetCode 5, longest palindromic substring, shares similarities in its use of a 2D array simulation, where optimization plays a key role in reducing space complexity. These problems can provide additional practice in tackling grid-based or propagation-style challenges. Finally, let's discuss some alternative approaches to solving the Champagne Tower problem. A brute force simulation is the most straightforward method. It's easy to implement but uses O(n²) space due to the full 2D array. This approach is suitable for smaller tower sizes where memory isn't a constraint. A memory-optimized simulation, on the other hand, reduces space complexity to O(n) by reusing rows or using a temporary buffer. While slightly harder to implement, this method is ideal for scenarios with larger constraints where optimizing memory is critical. Lastly, there's the option of using a mathematical approximation. This approach is typically much faster but may involve deriving a closed-form solution or accepting less precision. It's a good choice when approximations are acceptable or when performance is the highest priority. Each of these approaches has its trade-offs, so the best choice depends on the constraints and requirements of the problem. Great job! We've covered the Champagne Tower problem and discussed its key insights and solution strategy. Remember, simulation problems offer excellent opportunities to practice breaking down complex tasks. Stay curious, keep practicing, and see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!